Hello, pre-calc honor students. Here with 13.4, limits of infinite sequences. And our objective is to find or estimate the limit of an infinite sequence or to determine that the limit does not exist. Let's look at the sequence defined explicitly as t sub n equals 1/2 to the n power. So the first terms of this sequence then are going to be when n equals 1, 2, 3, 4, 5, 6. When n equals 1, t sub n then is 1/2. When n equals 2, we'll get a 4th. When n equals 3, the third term will be an 1/8, and then a 16th, and then a 32nd, and then a 64th. Keeps getting smaller and smaller. There's our sequence. Now clearly, as n approaches infinity, the terms of this thing get very small and approach 0. We call this a limit. The limit of 1/2 to the n as n approaches infinity is denoted like this. The limit as n approaches infinity of 1/2 to the n, that's how it's denoted, and it equals 0. A limit is something that terms in an infinite sequence are getting closer and closer to, but there's a little more to the concept. What is the limit of 1 plus 1/2 to the n? Well, we can look at some terms. If n equals 1, 2, 3, 4, 5, 6, let's look at that same set of n's again. We put in 1, we get 1/2. We put in 2, we get 1 1/4. 3, you get 1 1/8. 4, you get 1 1/16. 5, you get 1 1/32. 6, you get 1 1/64. So let's fine tune our limit, because now the limit over here isn't 1, even though we could say we're getting closer and closer and closer to 0, and we are, but the thing is, you're getting closer and closer and closer to 1. 1/2, here's 2, start with 1/2, 1 1/4, 1 1/8, and so forth, like that. So, here's our fine-tuned definition. The limit of an infinite sequence is the number that the terms of the sequence are getting arbitrarily close to as n approaches infinity. By arbitrarily, that means if someone picks any error, you can get that close. That close to the limit if n is big enough. If n is big enough, you can get that close to the limit. So here in that previous example, notice we can't really say the limit's 0 here, because someone said, well, can you get within 0.1 of 0? No. You're never going to get below 1. But we can say the limit of this is 1, because if I say, okay, get within 1/10 of 1, well, you can just go out here to the 4th term. Get 1 to the 1,000,000th of 1, well, you just have to go further out, but you eventually will get that close to 1. Up to the limit of 1 plus -1 to the n. Let's look at some values on this n. It's 1, 2, 3, 4, 5, and so t sub n then, when we put in 1, we'll get -1 to the 1 over 1, so you just get 0. When you put in 2, though, you get 1 1/2. Then you get a half. When you put in 3, we'll get 1 minus a third. I'm sorry, this is 1 1/2. And then when you put in 3, you're going to get 2/3. And then when you put in 4, you're going to get 1 1/4. And then when you put in 5, you get 4/5. So you can see how we're kind of dancing around here. When we put in 1, we're at 0. 2, we're at 1 1/2. 3 we're at 2/3, 4 we're at 1 1/4, 5 we're at 4/5. And see how this limit is getting closer and closer and closer to 1. Because basically this part is getting closer and closer to 0. But we're approaching 1 from different sides of 1. And that's what makes this one a little different. Okay, find these limits. The limit as n goes to infinity of the sine of 1 over n. Now in these first few examples, I'll let you go ahead and use a calculator. And I've got a spreadsheet set up here. Let's try and figure out the sine of 1 over n as n goes to infinity. Let's break out our spreadsheet. The sine, what we're doing here, yeah, the sine of 1 over n. Okay, let's take a look here. This will be n, and this will be the sine of 1 over n. So let's set up a bunch of values here. Here's 1, and then we can copy this down, equals the previous term plus 1. Oopsie. Previous term plus 1. There we go. Copy that down for a bit. And so now this will equal the sine, and that function's in there, of 1 divided by whatever number's in this box. And you get something like that because it's doing the sine of 1 there. Copy that down now. And we can see that our values are getting smaller and smaller and smaller. But are they approaching 0.04 or are they approaching 0? What we can do now is, let's have our next few terms be this. Let's equal the previous term, the previous index, times 2. Hopefully we can get this. Oopsie. This equals this index times 2. There we go. And now we can go further down the sequence. Control G. So you're getting some very big numbers because you're doubling it. And see how we are getting very close to 0. Okay, so that's how you can pursue it on a spreadsheet. The calculator works well as well. All right. Now let's look at this one as well. Limit as n goes to infinity of 0.99 to the n power. So we can go back to our spreadsheet, and now let's call this 0.99 raised to the n power. And so we change our formula here and say that this is equal to 0.99 raised to this n power, and copy that down. Let's go all the way down to what we had before. And essentially goes to 0. So at first it doesn't really change that much, but as we head off to infinity, it's definitely getting closer and closer and closer to 0. Okay. Okay, let's review what we just talked about, because we just did things with calculators and spreadsheets. Can you do this without a calculator or spreadsheet? Well, we could look at it this way, as the limit as n goes to infinity, the sine of 1 over n, as the sine of the limit as n goes to infinity of 1 over n. And so that's the sine of something that's essentially 0, and the sine of 0 is 0. So that's one way you could do it without a calculator. Let's try this one too, 0.99 to the n power. 0.99 to the n power. Well, the whole point is we're going to say that this equals 0 because 0.99 is between 0 and 1. And whenever you take a geometric series and have a common ratio less than 1, the terms will get smaller and smaller and eventually approach 0. So we're going to fine-tune this now with one of our theorems here. If the absolute value of r is less than 1, then the limit as n goes to infinity of r to the n equals 0. That'll be very handy for doing other problems. So find these without a calculator. Well, our trick here is to try and use this idea over and over again. So what we can do is multiply this by 1 over n squared over 1 over n squared. So we get the limit as n goes to infinity of 1 plus 1 over n squared all over 2 minus 3 over n. And now as n goes to 0, as n goes to infinity, these terms fall out. So let's write that down, that these go to 0. Just those terms that have the over n in them. So that we end up with 1 half. Something like this now too, we can do something similar and multiply by 1 over n cubed over 1 over n cubed. So we get the limit as n goes to infinity of 5 over n plus the square root of n over n cubed all over 3 plus 7 over n cubed. Now in this case we see that all three of these terms go to 0. And we end up with just basically 0 plus 0 over 3 plus 0, and that just equals 0. So we get 0 for a limit there. Now we had a trick for this before, and we'll get back to that again, about how you can predict in rational functions. But first let's look at sequences that have limits are called convergent, and if a sequence doesn't have a limit, we call it divergent. Divergent. Here's an example of a divergent sequence. Our first term goes to half, second term to negative 2/3, third term to 3/4, fourth term to negative 4/5, fifth term to 5/6, and we can see how they're not getting closer and closer. I mean, every other term is getting closer to 1, and the other terms are getting closer, the even terms are getting closer to negative 1. But that's what we call divergence, so we do not have a limit there. And you can't just say plus or minus 1 is the limit. This has no limit. Now, some infinite limits are what happens as we look at this sequence, which basically starts out at 3, and then we put in 2, and we get 7, and then 11, and then 15, and then 19, and then 23. This is going to head off to positive infinity for its infinite limit. And negative 10 to the n will be negative 10 to the first, which is negative 10 squared, which is negative 100, negative 1,000. This one is heading off to negative infinity. Those are examples of infinite limits, like you take the limit and you give it as an answer one of the infinities. Now let's show that this limit is infinity. Well, it's the limit as n goes to infinity of 7n cubed over 4n squared minus 5. So we can multiply top and bottom by 1 over n cubed. See what that does. Or 1 over n squared. And we get the limit as n goes to infinity of 7n over 4 minus 5 over n squared. Well, this part will approach 0. But then we're basically looking at 7/4 of n. Oopsie, let's get a better pen here. Looking at 7/4 of n, which is just a line, and so this is going to approach positive infinity as n goes to infinity. Now, let's recall our work with rational functions so you can come up with some decisions on this much faster. If you've got a rational function, a ratio of 2 polynomial, then if the degree of p and n is, in this case, less than the degree of q of n, so you got 7n cubed, you got a third degree over fourth degree, then the limit is just going to be 0, because the bottom will grow faster than top, so this is just 0. If the degree of p of n is equal to the degree of q of n, and that's what we have here, we have a fourth degree over fourth degree, then the limit is the ratio of leading coefficients, so you can just pluck those off of there. And I'll let you do that without going through the whole proof of multiplying the top by 1 over n to the fourth and the bottom by 1 over n to the fourth, and eventually you just get the 7 to the 4 and all the other terms go to 0. You can just use this trick. Finally, if the degree of p of n is greater than the degree of q of n, then your limit is going to be one of the two infinities. And in this case, is this going to go to positive or negative infinity? Well, we can look at the leading coefficients. It's basically going to become roughly 7n to the fifth over 4n to the fourth, which is 7/4 of n. So it's going to act like a line, and with an increasing line as you go off, as n goes to infinity, f of n, or in this case, the limit is going to approach a positive infinity. So in this case, we chose the positive infinity. Give an example of a sequence whose limit is negative infinity. Well, the limit as n goes to infinity of, we want to make sure that the degree on top is higher than the degree on the bottom, so n cubed and n squared plus 1, let's say n cubed plus 3n plus 5. But this is going to approach positive infinity. We can just put a negative coefficient here on this, and now this will approach negative infinity. Okay? Flange out.